Actually have a Dropbox folder, so it's pull that up. Does anyone have any specific questions that they want to go over before we start the meeting? Please let me know. So then do those. That's gonna be, let's see,
Someone said big O notation and proofs.
big O notation and proofs. Okay. So let's start off with big O notation. See if I can find big O notation. Midterm review sheet,
There's a sample one, the big O of n log n factorial, if you want to start with that.
big O proofs. Sounds good. I'm just trying to find the question because she doesn't, in her Dropbox, she has the PowerPoints, but they're all PowerPoint like documents. You gotta like give me a second. Chapter 2. What do you mean download? All right, let's download it. Well, let's do the textbook. So big O notation and proofs, you said, right?
Yeah.
All right, let's start sharing screen. All right, everyone can. It's only 23 pages. Oh, a lot of pages. Okay, so let's go to big O notation, algorithms, growth of functions 3.2. That's going to be page 216. Can't she actually give the problems themselves? It makes no sense. Okay. Algorithms, growth of functions. Okay. Unfortunately, I don't need you anymore. All right. Okay. So, does everyone know the whole idea of big O notation, or does anyone want me to go over that as well? Let me try to find the proof.
I think let's go over it as well. Just kind of the difference between big O, big theta, big omega.
Sounds good. Okay. So let's scroll up and show big O notation right here. So the whole idea of big O notation, right, is this, right? Cool. Is we want to bound some function. So we're given a function f of x, right? We say that it's big O of g of x if we could find some constant c, right? Such that that c times g of x, it's always going to be greater than f of x whenever x is greater than k. So in other words, you might see like k is like x0, right? This is a starting x value, right? So this is just an upper bound, right? So if you want to see it graphically, right, think of this as f, right? We're just going to say that it's bounded by this function, right? So this is g, that's f, this is f. And the whole idea is we want to bound f by some function that's always growing greater than it, right? Other notations such as big, I think they have it here, big omega, big omega, big theta. I think even little o. But those are different. Usually the most popular and the most useful is big O notation. Especially like when you go later on in your careers in computer science, you'll see when you create like algorithms and you do your code, it's useful to know the worst case runtime of any function, right? Best case is useful, and usually a tight case is useful, but worst case usually gives like the best estimate, right? You always want to like overestimate and just like be safe. Right, so let's also go over big. Let's see if they find the big omega and big theta soon as well. Is everyone okay with that? Does anyone have any questions? We'll show like how to find these values C and K in a bit. But does anyone have any questions about the whole idea of big O notation?
You guys can type questions in the chat, by the way. I'll be checking that, so feel free to ask any questions you got. That example 4 you could kind of go through.
Sure. So let's actually, yeah, let's go through example 4. So we want to show that 7x squared is big O of x cubed, right? Okay. So let's prove this first part. 7x squared is big O of x cubed. Pretend you can't see the solution. Okay. Right. So we know that f of x is 7x squared, right? And remember, we can choose k. So if we choose k, this will impact c as well. Right. So let's say we want to prove that it's big O of x cubed, right? So if I choose k is 7, right? Then I plug in 7 for here. I get 7 times 7 squared is less than, remember, I want to prove, let me just backtrack a bit. We want to prove that this function, 7x squared, is less than or equal to x some c times x cubed, right? So if I choose k is 7, or actually, yeah, let's choose k is 7 here. Just want to show something. So it's going to be 7 times 7 squared is going to be less than or equal to c times 7 cubed, right? And then over here is just a matter of solving for c. We got 7 times 7 squared. Well, in the end, that's just 7. Move up here. 7 times 7 squared, that's just 7 cubed, right? There's 1 and then 2 sevens here. 7 cubed. That's less than or equal to c times 7 cubed, right? And if I divide both sides by 7 cubed, I get 1. C is greater than or equal to 1. Or actually, we don't even need the equal sign because we're trying to solve for c. So we could set this equal to. If you're trying to find out what c is, you set them equal to and you solve for c. Then you get c is equal to 1. Here. All right. So we see here that if we choose k is 7, then we could say our c is 1. And thus we could say that 7x squared, this is like the more formal way of saying it, 7x squared is big O of x cubed from k equals 7, right? So this is basically saying x greater than or equal to 7 for all x greater than or equal to 7, where the constant c is 1. Okay. And I want to show a different way we could do this. So we could, because this is where I say it's flexible, because you don't need to choose k is 7, right? If I choose a different k value, then that means that we could also choose, that would impact what our c is, right? And some values we can't. So then let's say k is 1. K is 1, right? So what does that mean? That means 7x squared, 7 times 1 squared, 7 times 1 squared This be less than or equal to some c times x cubed, right? In this case, x is going to be 1. So c times 1 cubed. So we get 7 times 1 squared is 7. So that's what this equal to. C times 1 cubed is 1. So we see that if we have another case where k is 1, we would need to choose c equal to 7. Right? So it would be the same idea. 7x squared is big O of x cubed. But instead of starting from k equals 7, we start from k is equal to 1. And then if that's the case, our c would not be 1, our c would be 7. Does anyone have any questions on how we did that, the thought process behind it? If you do have questions, let me know. I'm more than willing to go over it again.
Sorry, I had a question.
Mm-hmm.
So why did you change the less than or equal to just equal to C?
Because we're trying to find the value of c, right?
Yeah.
So we like if you want to find the value of c, you just set it equal to, and then you get the value. You just solve for c.
Okay, all right. Thank you.
Mm-hmm. Right, because we're just trying to find one value of c. Any questions?
Someone in the chat just asked if you could go over it again.
Okie dokie. So we want to prove that 7x squared is big O of x cubed. What is the definition of it? That means that 7x squared is less than or equal to some c times the second function, which is in this case x cubed, right? For some k, right? Some k value. And remember, we could choose the k value in the terms of the function. If you want to see this in terms of like graphically, it doesn't matter. Like, say if this is it's green, that's green, it has a nice green. Say if this is the function, right? And this is our second function, g. Right. It as long as there is some value right here. Right here. This is our k in this case. What happens before k, we don't really care about. It's what happens after k. After k, we see that the purple function is always greater than the green function. So as long as we can find some k value, like we get to choose this k value. As long as we can then find some constant such that the purple function is always greater than the green function, then it's big O. So in this case, we can choose k to be any value. So let's choose k to be, I don't know, I'm feeling like, let's choose k to be 5. Why not? Right? Based on this k value, we can then choose a constant, right? Because what we do is we plug this into x, right? So we get 7 times 5 squared. This is not going to be as pretty of a number. It's going to be a fraction. It's less than or equal to c times 5 cubed, right? And what do we get? We want to solve for c. We want to find what c is. So we turn this less than or equal to sign into a equal sign. And we do this. We divide both sides by 5 squared. Get rid of the 3 here. And we get that 7 is equal to c times 5. For everyone wondering about the chat in the recording, thank you, Lauren. I'll also, like, at the end of the meeting, I'll show you guys where the recording will be posted. So don't worry about that. We get divide both sides by 5. We get 7 over 5 is c. Right? So even though it's a fraction here, it still counts. You see that for now, we could say that if starting at k is 5, so in this case, k is this value. This is k is 5. We see that, well, we see is a bad word to use here, that for k equals 7 over 5 times x cubed, this will always be greater than or equal to 7x squared from 5, right? So this purple function is 7 over 5 x cubed, and this green function is 7x squared. So it's always going to be greater than 7x squared. Does that make sense? Is everyone okay with that? This is the first part. This is how you prove usually big annotations. Similar process. Once again, this is like what you choose for K is completely up to you. Right? That's given like the freedom. Based on what you choose for K, you then choose. Like you would want to choose like a smart value for K though, usually like small numbers like 1, 2. You don't want to get like K is like 1,000. That would be like very not good, like function wise. Like you don't want to calculate all that. But yeah, K5 is not bad. You get 7 over 5. It's not bad of a constant. If everyone's okay, let's move on to the second part. And this is like another part of this big O notation proving that something is not big O of something else, right? Similar question here. So I'm just going to do this one. And for these types of proofs, you want to use a proof by contradiction, which I'm going to write up here. All right. So show that x cubed is not big O of 7x squared. X squared. Okay. All right. And let's do this. So assuming this is true, so this idea of proof by contradiction. Proof by contradiction. Assume it's true, and then show it leads to something stupid. Okay. Let's see if this is the case. So assuming this is true, so we could say that this is true for some, that means x cubed, what is the definition of big O? That means x cubed is less than or equal to some constant times the second function, which is 7x squared, for some k value, for all of it, x values greater than or equal to k. Yeah. For all x values greater than or equal to k. Okay? Is everyone okay with this then? This is the basic setup of big O notation. The first function less than or equal to the second function times c for all x greater than or equal to k. Okay? So let's solve for this. We got x cubed, c times 7x squared, just c times 7x squared. Let's divide both sides by x squared. Squared, x squared. We got x is less than or equal to c times 7, right? 7c. However, is this true? Is this true? Remember, c is a constant, 7 is a constant, x is a variable. Can you ever bound a variable by a constant? This is where I get user. No, you can't do that, right? This is not good. Can't do that. Oh, I think that's how they do contradiction simple. Then write two swords. Yeah. You cannot bound a variable by a constant. Right? So if you want to visualize it, this is a constant. A constant's always one line. And the variable is always going to go up, right? So there will come a point where the variable goes above the constant. So this isn't true. Contradiction. And thus, what we initially assumed, I'm sorry, assume it is. So what we initially assumed is false. And thus, it's not big O. Is everyone okay with that? Does anyone have any questions about this? We'll move on to like big omega, big theta, etc. But these are like these are like the main usages of big O. Proving it is, and then usually if you want to prove something isn't, you want to use big O notation. Not, I'm sorry, you want to use proof by contradiction. Assume it's true and then show us it leads to something stupid. This is what is stupid. You can't bound a variable by a constant. Any questions?
I think it also helps a lot to kind of know how much bigger something is compared to something else. For instance, you know, x is smaller than x squared, which is smaller than x to the third. Kind of knowing like all of those kinds of things. I believe in her class she kind of showed a graph with like a bunch of different common functions.
There
It's
it is.
oh wow. Okay, perfect. Yes, I would definitely like try to memorize this because it's good to see like on the bottom you have 1. This is a constant, right? Then right above the constant you have the log of n, right? We know logarithms, their rate decreases over time. You have n, right? You're just normal variable. Like in the example we had x before. We have n times log n, which is a little bigger. Then you have your polynomials, right? You have like n squared, you have like n to the third and all that. 2 to the n exponentials are always going to be quite high. And then the biggest usually is always going to be your factorial. Because think, what's a factorial? It's multiplying every number that's below that n point. So that's always going to be going up really high. So yeah, definitely memorize these guys.
My bad, Chad. I was trying to rest the voice. But yeah, thank you, Lauren. This is like, if you want, memorize this graph. I doubt that she's gonna ask like for these higher functions, like 2 to the n squared. But anything from 2 to the n and n factorial, anything from n squared, like to here, all fair game. And in general, there's a rule where if you're given, I think right here, right? So if we're given a polynomial where it's like constant 1 times x to the n, constant 2 times x to the n minus 1, etc. So think about it like this, like x cubed, like 4x cubed plus 11x squared plus 3x minus 5. Then the highest exponent is what's bounding the entire thing. So this entire thing is big O of x cubed, right? Because that's the highest exponent. And there's a way you could prove it. Like you show this. I think I learned this in 313. But in general, if you remember this rule, you could just use it, right? So x cubed, 4x cubed, highest exponent, it's big O of x cubed. Okay. So that's for polynomials. Polynomials are usually easier to figure out. Logs. See if there's anything else you need to know. Well, I think these couple of these for the logs. Median. This one's useful. There's one with the logs, I think. In general, if you have any polynomial, it's always going to be big O of logs. Logs tend to always go slower than polynomials. So that's also useful. I'm just trying to point out useful things to know. Because in the end, I'm pretty sure the exam's most likely going to be of these. Right? She might tell you to order them or something. Or like trying to prove something like something simple, like either a polynomial, which in this case, let me just actually go through this. So let's say we're given this function 4x to the third minus plus 11x squared plus 3x minus 5 is x cubed. So what I like to do is I like to chat.
Yeah, someone posted an example of the ordering function, so maybe we could kind of go through that.
Okay, sounds good.
If you want to just finish this example, like how you got to big O of x cubed, since that's the largest power, right?
Okay. So let's do this. I like to split up each term. So let's do 4x cubed. This is always going to be less than or equal to 4x cubed. All right. Because they're equal, so it's always going to be less than or equal to. And it's going to be k is equal to 0. All right, why not? Then we've got 11x. I have 11x squared is always going to be less than or equal to, well, 11, if I choose k is 11, then it's always going to be less than or equal to x cubed, right? Remember, we could choose k. And then we got 3x. It's always going to be less than or equal to x cubed. Let's say k is equal to, k is 2. 3 times 2 is 6. 2 cubed is 8. Yep, that's true. 2. And we got minus 5. Actually, we got positive 5. Don't put minus. Positive 5 is less than or equal to x cubed. Once again, k is equal to 2. Right? Right. So now what I like to do is, since all of these on the left side added up is this, then I could, since they're all less than or equal to these, I can just add them up. So I get 4x cubed plus x cubed plus x cubed plus x cubed. That's 4, 5, 6, 7. So let's call this function f. So we got f of x is less than or equal to 7x cubed. And we just choose the greatest k. So that would be k is 11, just to be safe. For k equal to 11, i.e. all x greater than or equal to 11. All right, so that's like a simple, this is how I learned to prove these types of polynomials. Just look at each term, find it big O in terms of what we're trying to look for, and then combine everything and get the solution. Okay, does anyone have any questions? And this is why, in general, for any polynomial, it's usually big O of the highest power.
Yeah, I had a
I don't-
quick question.
What's up?
So in the first example we did, where it's like 7x is big O of x cubed, it would also be big O of x squared, since 2 is the highest power.
Yes.
Okay, cool. Thanks.
Where's that example? Yeah, but yeah, you're right. Because 2 is the highest power, you could, that's a fair point to make, because technically, right here. So I could say like 7x squared is also big O of, say, x to the 1000th. And that's perfectly right. And you could prove that. But the idea is that you want to, it's not, let me squared. And this is true, but it's kind of obvious and it doesn't really help us. So like if I say, because like this is like taking it to the extreme. If I say this function is big O of this function, you're right, but like that doesn't really tell me much about my function, right? And that's why we want to find like closer big O's. So you have 7x squared is big O of x cubed. And that's much better than saying it's big O of x to the 1000th, right? So even though on your exams, like you could say like, oh, it's big O of x, I don't know, whatever power you'd like. You could like go crazy, but like that doesn't help, and that wouldn't technically be right. Even though it is correct, it wouldn't be helpful. Okay.
Cool, thanks.
So
Suleiman, what does that say in the parentheses? K is greater than or equal to 11?
I'm sorry, I can't write k. This is x greater
Oh,
than or equal to
gotcha.
11, because that's why we choose k. K is our starting x value. Sorry about that. Let me look at the image we want to do. Slowest all left. Let's do this. Copy. Hold on. Okay. Give me a quick second. I'm gonna stop sharing. I'm gonna share again. Share. Okay. We want to order functions by order of growth. So this one, it's based off of the. Is this not good enough? So let me make it a bit bigger. There you go. So you want to look at each function and then kind of like, some of this is intuition, right? So let me just order it. So you got F1 through 10. So we got 1, 2. Actually, let's not do that. All right, let's order it here. Half of this is just logic. N factorial is always going to be biggest. This is always the greatest. So let's say this is 1 through 10 is the greatest. Let's label it like this. This is 10. It's the greatest. Nothing will ever beat N factorial. If your program runs an N factorial time, no offense, buddy, but look for a new job. That's the joke I tell my friends. Right? N factorial is always the worst. And constant, even though you might see this as a big constant, this is always the fastest. All right? This is the fastest. So right off the bat, these two, you could use logic. And then comes a little bit less logic, but we got 2 to the n, right? This is going to be 2 to the n times n squared minus 1. If you look at these two functions, 2 to the n is always going to be second grader to like n factorial, but it's still really, really, really big. And if you take that big number and you multiply another number times it, this is all obviously going to be greater than this. So this is going to be 9th. This is going to be 8th. Right? So once again, part of that's logic. Right? And then we have this. So this, even though it's not 2 to the n, anytime n is in the exponent, then it's going to be a pretty large function. Then you just compare the bases. Right? If you want, you could take the log of both sides, right? So log of, so let's compare 1.5 to the n to 2 to the n. Log of 1.5 to the n, log 2 to the n, right? The n comes down, so it's going to be n times log of 1.5 and n times log of 2. And log of 2 is greater than log of 1.5. So this is going to be like this. But in general, anytime n is an exponent, this is always going to be greater than like polynomials and like other logs. Okay, so this is 7. Okay. Any questions so far? These 5 that I just pointed out, like mostly through logic. Constant's always going to be the fastest, and factorial is always going to be the slowest. These 7 through 9, you could do a bit of math to see that they're in that order. And then comes what we see next. So after 1, let's see the rest. This is going to be this. This is going to be 2, right? Logarithms grow pretty slow. And if you look at it graphically, they grow like this. Right? They go very slow. So if you take a log of a log, that's going to grow even slower, right? Than say like a log squared. This is number 3. Right? And it may like feel, you might be confused. If you're confused on like how I'm ordering these, like please like let me know. 'Cause like half of it's based off logic, right? Remember the textbook we saw, like the image, and half of it's based on like within like the specific grouping you have. You just gotta do a little math. Like we have the little group of 7, 8, and 9. Once you do a little math, you see that 1.5n is going to be less than 2 to the n, and 2 to the n is always going to be less than 2 to the n times some other number, right? And then we see there's another small group. So that's the logs. Let's say right here. So 3, this is going to be this one, this one, this one. This is going to be 4. Right? 1, 2, 3. Yeah. Bingo. Yep. This is a log. So a log of a log is always going to go slower than log. This is basically like log times log. Log squared is just so log of n times log of n. And this is obviously going to go faster than if you take log of n. If you want to check that, once again, you could take the log of both sides. So we get log of n, log of n, and log of n squared, n squared. We see the 2 come to the front. So we get log n. Well, that compared to 2 times log of log n. And we see the 2 makes it so that this grows faster than this. Okay. And then comes this. Log n squared. Once again, because this is log n cubed, I'm sorry. Squared is going to grow slower than cubed. Then we have the extra n squared here, right? Any questions so far? Like I said, half of it is just logic and kind of like splitting it up into groups, and then within the groups, you'll have to see, like, you'll use a bit of math in order to get the differences between them. Okay, and we have one more group. We got this f2, then f of 8. We see that f2, they're both n cubed, right? But remember what I said. This is log n squared. This is n squared. Any polynomial will always grow faster than the log function, right? So this is always going to be faster. This is going to be, whatever number, we're on 5, right? 5, this is 6. Right. That's goes back to that rule. 17n squared is always going to be faster than n times log n squared. And that's the ordering. Does anyone have any questions? Does anyone want me to go through it one more time if they're confused?
I think memorizing that graph would help a lot here.
Yeah.
You can
Part
just
of
group
that's
them
just-
together and then you just
Yeah,
separate.
that's the whole idea. Once you like see like the numbers and you memorize the graph, like right off the bat, you know that n factorial, super slow, constant, super fast. Then the logic is grouping them into groups. So you see there's a groups with logs. Okay, you got these. Then you have groups with polynomials. Then you have groups with exponentials. And then within those groups, you like order it like in the groups. And then it becomes a bit easier. Okay. Is everyone okay with this? Any questions?
Do you guys feel good with big O? Because if that's the case, then maybe we can go over to big omega and big theta. They function pretty much the same way, except big omega, instead of being an upper bound, it's a lower bound. So you kind of just flip the sign around. And big theta is kind of like a estimation like between the two, in the sense that if your big O is also big omega, then it's like you kind of get right in the middle there. So, Suleiman, you want to go over an example of those, you think?
Sounds good. So if everyone's okay with this, I'm gonna oh, it's gone. Okay. So I'm gonna switch screens once more. Someone say Towers of Hanoi. Sure, we'll go over Towers of Hanoi. Why is F2 not number 5?
In the picture, why is F2 not number 5?
It probably is.
Are you saying that why F2 and F8 are tied? It's because they have the same um uh sorry, they have the same like term, like the highest term is n cubed. So that's why they would be in the same tier, so to speak.
Yep. Remember this rule? Theorem 1? You always look at the highest exponent.
Yeah, so even though you have that 8x cubed versus, just regular x cubed, they both have that same term. So because of that, they're kind of in like the same tier group, you can say. Yeah.
Yeah.
Also, you could always graph these guys, by the way, if you have a graphing calculator on you, and you can kind of see, how they kind of are in that same tier in a sense. I don't think you're allowed a graphing calculator on the exam, but yeah, for now you can kind of like see it visually too.
Okay, so we got big omega and big theta. Before we do that, I'm just gonna quickly bring up these two rules. Okay. right here. So if we have two functions, this is like usually when you have two functions. Oops, sorry. I think that's so if we have two functions, right? I'm going to briefly go over this. If you add two functions, so we have f1 is big O of g1, f2 is big O of g2, right? If I add both functions, then you just take the max of g1 and g2. Quick example of this is say f1 is big O of x, let's say x cubed, and f2 is big O of x to the fourth, right? We don't know what f1 and f2 is. But if we add them, this, remember, f1 is basically saying that f1 is less than or equal to some c times x cubed. This is basically saying f2 is less than or equal to some c times x to the fourth. If I add these two functions, then I just take the greatest of these. Because if it's less than or equal to x cubed, it's going to be less than or equal to x to the fourth. Right? That's why it's going to be g of x is the max of both functions. Right? And that's based off that, you could just say the same thing, right? If both functions are big O of the same, then their sum is going to be big O of the same of g of x. Right? So similar. So if f1 is less than or equal to c times, say, x cubed, and we know that f2 is less than or equal to some c times x cubed. If I add one, f1 plus f2 is less than or equal to c x, let's say this is c1, c2, c1 x cubed, c2 x cubed. Factor out the x cubed, I get x cubed times c1 plus c2. c1 plus c2, that's just another constant, let's say c3. And thus we've proved this, right? Their sum is also big O of x cubed. Okay. And then we have with product, this one's a bit more obvious. If they're big O of two separate functions, then the product is going to be big O of the product of the functions. Right. I feel like this one's a bit more obvious than the last one. So yeah, I just wanted to briefly go over those. Okay. Big omega notation, big theta notation. So big omega is technically the opposite in that respect. Whereas in big O, we wanted to find an upper bound. This is F. Big omega finds a lower bound. Right. Right. So it's going to be our K value. And we see that this G is always less than or equal to F. Right? F is big omega of G of X. If you want to rewrite this, this is also technically saying that G is big O of F of X. Okay. So if it helps, you want if it makes it like clear that way, you could think about it in reverse and say that G is big O of F of X. Right? That's the same thing as saying F of X is big omega of G of X. All right, so if you have an example here, we want to prove that 8x cubed plus 5x squared plus 7 is big omega of, let's say, G of X of X cubed. This is obvious because if we choose C is equal to, I don't know, in this case I choose 8, it works because 8x cubed plus 5x squared plus 7 is always going to be greater than or equal to 8x cubed because of this extra 5x squared plus 7. Right? There you go. Remember, like I mentioned here, they also say G of X is X cubed, big O of this. Bingo. Big theta is this both of them combined. Right? So you want to prove F of X is big theta of g of x if f of x is not only big O of g of x, that also f of x is also big omega of g of x. Basically, if you were to like see this graphically, it's kind of like saying they both grow in like a similar rate. Yeah, like that. Okay. So you multiply by one constant, you get a lower bound. When you multiply by another constant, you get an upper bound. Okay. Right here. Same function, different constants. So this will usually give like a tighter bound. And this is usually achieved if they're like, when you think of polynomials, usually when they're the same powers. So you could say if x squared plus 1 is big theta of x squared. Because if I choose c to be 1 times x squared plus, not 1 times x squared, is always going to be less than or equal to x squared plus 1, right? Because of the plus 1. And if I choose c to be 2, then x squared plus 1 is always less than or equal to 2x squared from, let's say, x is 2, from k is equal to 2. So k. Okay. I'm going through these two a little bit quicker because you might get a question or two of them on the exams, but in like later on, when you're talking about algorithms and stuff, you usually deal with more big O notation rather than big omega. But they're still useful. So, does anyone have any questions? Does anyone want me to do an example of these? They have an example. Do you all want me to do an example?
Yeah, please, can you do an example? Thank you.
Okay. Let's do this one. Alrighty, so we want to show that 3x squared plus 8x log x is big omega, not big omega, big theta of x squared. Okay. Let's first prove that 3x squared plus 8x log x is big O of x squared. Once again, this is pretty easy because if you go back to our it'll talk about big O, we just look at the polynomial. So it's going to be big O. This. So we could say that this is C is equal to 4. I don't know. Let's say 4. So we have 3x squared. We know 3x squared is less than or equal to 3x squared. All right. And we also know that 8x log x, this is going to be less than or equal to x squared because polynomials always grow faster than logs. So we just add them together. We get that 3x squared plus 8x x log x is less than or equal to 4x squared. And let's say k is 8, just to be sure. Or do it next to log. 10. Yeah. K is 10. Right. So that's the first direction. Ooh. We want to prove the second direction. That this is also the case. We want to prove that 3x squared plus 8x log x is also big omega of x squared. So once again, if you want to think of this in like an easier way, you say that x squared is big O 3x squared is less than or equal to. Are you talking about this? This part right here? Yeah, 3x squared is less than or equal to 3x squared. They're the same function. Three x squared is less than or equal to 3x squared. It's like f of x. It's like is 1 less than or equal to 1? Yeah, because they're the same thing. No, it's less than or equal to. You see that? I'm not saying this. We don't need to prove just strictly less than. As long as it's less than or equal to. Does that clear it up? Yeah. We can't say just strictly. 1 is not strictly less than 1, but it's less than or equal to 1. So the same thing. Anything is less than or equal to itself. So just basically, let me make that a bit more obvious. You're right. My fault, chat. Less than or equal to. Right? Does that make it better? It's not strictly less than, it's less than or equal to. Okay. So now here we want to prove that if we want to think about it in terms of big O, that x squared is big O of 3x squared plus 8x log x. Well, once again, just look at the constants. We know that x squared, heck, if we choose our constant to be 3, that means 3x squared is always less than or equal to 3x squared plus 8x log x because of this part right here. Because we're adding extra to the right side. That means this is always, the left side's always going to be less than or equal to the right side. Okay. So that's this direction. And thus we've just proven that 3x squared plus 8x log x is big theta of x squared. I remember how I said before with big theta, it's usually like the highest signs of polynomials being the same right here. Right? We can't say that this is big theta of x cubed, because then we would get that this is not big O of x cubed from a previous proof that we did. Okay. Does anyone have any questions? I have been yapping about big O for a long time. Any questions? Any questions? I think people wanted to go over. If you guys have no other questions, I think let's transition to, does everyone want to do proof by induction?
There was a request for recurrence relations.
Recurrent relations. Okay. So induction first, then recurrence relations, or recurrence relation first, and then induction? Can I do a poll here? I can do a poll. Hold on. Wouldn't mind induction. Induction first. Ann Smith usually does polls here. I don't know how she does a poll. We'll figure that out. Okay, so we'll do induction first, and then we'll talk about recurrence relations. It's the infinite ladder analogy. Yo.
Oh my
It's not-
gosh, it's Suleiman's favorite thing, the infinite ladder.
I love the infinite ladder. That's how I learned it. Okay. So, induction. The whole idea of induction is that when you want to prove things for an infinite amount. So like it's easy to like say prove x for like say from 1 through say 1,000,000, right? How many zeros are in 1,000,000? 6, right? Easy. We just plug every single thing in. But say I want to prove x. I say this is a statement, right? For any n. Well, n has no bound, right? Say these are all the natural numbers. Natural. These are natural numbers. There's an infinite amount. So I can't prove an infinite amount of cases, which is why we need induction. And the whole idea of induction is infinite ladder. It's an infinite ladder to heaven. It's heaven right here. It's this little sun smiling. Very nice. Very nice. It's an infinite. You can't prove that any individual step. So how do you do it? You just prove that as long as you could go to the next step, you could climb the ladder to heaven, right? So how do you do this? This is the basis step. You can't climb the ladder if you can't get on the ladder. You first must get on the ladder. That is this part. Basis step. All right. We must first prove that we could get on the ladder in the first place, i.e., we could even start using what we're trying to prove. And then the whole idea is, if we can be on, given we're on any step of the ladder, we can always go to the next one. Right? So that's the whole idea. Using this, we can then say, oh, I can be on rung 1000. I can then go on rung 1001. Right? Because that's how you prove infinite things. Right? If I were to like prove every single step, say I proved from rungs 1 through 1000, then someone will come up to me like, how do you get to rung 1001? And I'll be like, oh, I don't know how to plug it in. Right? With induction, I can say that any step I'm on, and go to the next one, and then the next one, and then the next one, and the next one, up until the little sun. Okay? Is everyone okay with the idea of induction? We'll do a few examples. We'll do like 2 examples. Induction. Okay, so a little bit more about induction. Ooh, this is another good. Whoa. I like this analogy. Dominoes. Oh, that's nice. Okay. When it comes to induction, there's a template. Okay. I would say the most important parts is define your function. All right. In basis step, you always need a basis step. You need to prove it. And I'll show like 2 different types of induction where it's like 2 different basis steps, but basis step is like proving it for the base cases. Inductive step is assuming this. It's basically this. Right? Assume P is true for some arbitrary fixed integer, K is greater than or equal to B. We need to prove this. And then step 5 is like the math part of it. We prove P of K plus 1 using P of K. And then you don't need that. Then we're good here. Then you just say the proof. And you put QED. For the mathematicians out here in this class, I think you know what QED does, what QED means. Basically means quite easily done. Or you'll usually see like a little square. Right? So let's do a few examples. Okay, this is my favorite example. Show that if n is a positive integer, then 1 plus 2 plus ... up until n is equal to this. There was another way that someone else proved. I think the mathematician Gauss, when he was in 5th grade, proved this. It was insane. The proof's insane. It's hilariously fun. Anyways, let's prove induction. Prove it with induction. So I'm not going to write out every single step. On your exam, please be sure to write out not like everything here, but like the important stuff, like what we're trying to assume, the basis step, the inductive step, hypothesis. This part, the mathematical, this is important. This is like the whole meat of the proof. And then you could, yeah, just write by mathematical induction, P of n is true for all integers n with n greater than or equal to b. Okay, let's get cracking. Sorry, my voice is starting to hurt after talking for an hour straight. Okay, this is our function, P of n. Our base case, let's say, they said using 1. I don't like to use 1, or like I like using numbers greater than 1 and 2, like for these situations, because 1 and 2 are like really weird numbers. So let's use 3. All right, so 1 plus 2 plus 3 is equal to 3 times 3 plus 1 is 4 over 2. 3 over 4 is 12. 12 over 2 is 6. And what we see, 1 plus 2 is 3. 3 plus 3 is 6. So it's true. Passes the base case, right? So this is where you would write out this part right here. So like, right here, base case, right? Prove P of 3 is true, yada, yada, yada. Boom. That's like a few points right there. Now the inductive hypothesis. Right, inductive hypothesis. So we assume that P of K is true for some K value greater than or equal to B, i.e. 1 plus 2 plus dot 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 plus, let's say K is less than 2, plus K, that this is equal to K times K plus 1 over 2. Okay. We want to show that P of K plus 1 is also true. So let's do it here. All right, so let's do it here. So we know that P of K plus 1, this is the math portion of it. K plus 1, we want it to look like something like this. So it's going to be K plus 1 times K plus 1 plus 1 is just K plus 2 over 2. Okay, so now we use this. Well, what's P of K plus 1? That's just 1 plus 2 plus dot 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 plus K plus K plus 1. Right. What do we see? This part is P of K. Right, so let's use that. We know that this part is P of K, so that's going to be, by our inductive hypothesis, this is equal to K times K plus 1 over 2. I can't draw a straight line for my life. Over 2 plus K plus 1. Okay, so now, mathematical step, I want to combine this, just multiply this by 2 over 2. I get K times K plus 1 plus 2 times K plus 1 over 2, right? I can factor out a K plus 1 from both terms. I get that K plus 1 times K plus 2 over 2. Right? Yeah, there you go. We proved what we want to. Here you go. We want to show this. K plus 1 or K plus 1 times K plus 2 over 2. K plus 1 times K plus 2 over 2. And we're done. This is where, like you write, through mathematical induction, P of n is equal to n, yada, 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 for all integers in n. Yeah, there you go. And that's the proof. Does anyone have any questions about the proof? Any questions at all? This is basically the crux of in mathematical induction. Damn, I did not think I was going to use that word today. Huh, check that off the bucket list. Any questions about mathematical induction? Is everyone good with this? Okay. So, you have this proof right here. There. Okay, plus 1, yada, yada, yada. Okay. Once again, most of these follow like the same format. So like the main part of it is like using the inductive hypothesis to prove it. Let me find a different one. These are all pretty much the same. Not harmonic series. There's a different one I want to show because no. Let's do it here. The blank page. Blank page. Very nice. I want to show a different type of proof because there is a this type of induction, scroll up a bit. This type of induction has one, you can usually prove it with one base case, right? And we see that by using any k, we can prove k plus 1. But some cases we can't do that. Let me show you why. So this here, okay. Say I want to prove that any number n, horrible n, any number n greater than or equal to 12. I can prove to you that n is equal to some integer 4k plus 5, say L. That's 4 times A times 5 times B. Right? So I want to prove this. Okay. Any integer n greater than or equal to 12, I could just write it as 4 times some integer plus 5 times some positive integer. Okay. That's the base case. Base case. Well, if it's 12, this is equal to 4 times 3 plus 5 times 0. Okay. 13 is equal to 4 times 2 plus 5 times 1. 8 plus 5 is 13. 14 is equal to 4 times 1 plus 5 times 2. 4 plus 10 is 14. 15 is equal to 4 times 0 plus 5 times 3. Okay. These are our base cases. So this is, let me make this a distinction. In terms of your class, induction usually like you'll see like this. So this is also a different type of induction. This is what us mathematicians know as strong induction, right? Because we have not only do we have more base cases, the idea is we go back to our little magical ladder here. You usually use the fact, given I'm on any rung k, I can go to k plus 1. Strong induction assumes more. Given I was on any rungs from 1 through k, I can go to k plus 1. In most cases, when it comes to induction, you only just need these two cases, k plus 1 and k, such as here, right? We proved k plus 1 using k. But in this example here, I'll show you why we can't really do that. This is our base case. So now our inductive step, we want to prove that for any k, we know that p of k is true, right? So p of k is a can be expressed as any two numbers 4 times a plus 5 times b, right? Okay. And now we want to show that I could show k plus 1 is also equal to 4 times a plus 5 times b. Okay. I can't prove this with just k. K is equal to 4a plus 5b. All right, so 5, by the way, sorry. 5. You can't go from k to k plus 1. It's not like you're unable to do that. But what I can do is I could use k minus 3. Why k minus 3, you might be thinking? Well, we know, remember, this is, so we want to prove k plus 1. We know that a is equal to, we know p of k is true for all k from 1 through k less than n, right? And we have our base cases. We have 4 base cases. And now we could show that k minus 3 is also true. We know this is true because not only have we proven it with the base cases, we start at 15, we go minus 3, right? That's why we technically have 4, because I wanted to use this minus 3 here. Okay. So then how does this help? Well, I could add 4 on both sides. If I add 4 to k minus 3, I get k plus 1 is equal to 4a plus 5b plus 4. Okay. I can bring the 4s together. This is 4a plus 4 plus 5b. If I factor out a 4 from these, I get 4 times a plus 1 plus 5b. All right. A is an integer. We know it is. All right. So then a plus 1 is also a positive integer. And thus, we've just proven that k plus 1 is equal to 4 times some positive integer plus 5 times some positive integer. And thus, we have proven that this is true. All right, so this is the main difference between strong induction and weak induction. And I wanted to point this out because in some cases, or at least most cases, weak induction works. And it's pretty much, it suffices. We don't need really much to prove it. We just proved this. Sorry if it's a lot of drawings, but we just proved that k plus 1 is true using just k. But in other cases, it's more useful to have more tools to use. Right here, instead of using k, you use k minus 3, because we know this is true for all numbers up to k. From 1 through k, so we use k minus 3, and thus it makes our lives a bit easier. Okay. Does anyone have any questions? Any questions at all? If you want to take a screenshot, feel free. Any questions? Any questions? Everyone's.
Do you want to take a 5-minute break?
No, I'm good. I'll push through to the end.
Okay, yeah, I think we have about another half hour, so we're almost to the end.
And if that's the case, I think this is pretty much it with induction. Everything else usually follows the same idea of both. Is everyone okay with this? Does anyone want to take a screenshot of it before it's gone forever?
I mean, it'll be in the recording, so.
All right, so it's gone. Clear. It's gone. Okay. But yeah, most inductive cases are going to be of those two. Like this is like usually the best, like where you just use k to prove k plus 1. Some cases it's not enough. You might have to use like another something other than k. But yeah, that's usually it for induction. Is everyone okay with induction? Anyone have any questions before we move on to recurrent relations? Where is recurrent relations? There it is. No,
5.4?
5 point recursive algorithms. For recursive. Oh, okay. Is this just recursion? I wonder, I think if we go to Towers of Hanoi, it'll have it. Hmm. To improve set matrices algorithms. No, it's
If
not
anyone
on.
has any sample recurrence relations questions or anything taken from the slides, if you could post it in the chat.
Induction, counting, no. Relations. Oh, never mind, this isn't it. Does anyone have any questions they want to do? I'm trying to find where it, we have it in here. Recurrence relations 8.1 to 8.3. Oh, found it. Okie dokie. All right. Oh, okay. Found it. I think someone wanted to go over Towers of Hanoi too. Uh-huh. Bingo. Okay, so the whole idea of recurrence relations is technically this is how you could like this is one way you could show recursion through like a formula. So like if we have n months recurrence relation. Yeah, so basically this is an example. Recurrence relation is basically whenever a current value is based on previous values. So you're gonna have two parts. You're gonna have this as a formula, the recurrence formula. You're gonna have base cases. You need a base case. So you need F1. In this case, they have F1 is 1, F2 is 1. So it's gonna be for all n greater than 3. So we can use this formula to then get any value for n later on. So say I want n4, f of 4, right? This is equal to f of, this is not equal to 4, I'm sorry. This is equal to f of 3 plus f of 2. F of 3 is equal to f of 2 plus f of 1. F of 1, f of 2 is 1 plus 1. You get the base cases, right? Hopefully this sounds familiar because this is just technically just recursion. 2, f of 2 is 1, so this is 2 plus 1. So on the 4th month, the rabbits are going to have 3 of them. There's 3 rabbits. Okay. Right, and then we go with like Towers of Hanoi, right? So if you look at the Towers of Hanoi, basically you have 3 pegs and you want to move all of the discs from one peg to another peg, but you can't have it so that the lower, like the smaller one is below a bigger one, right? They have to remain in size order. Okay. What is here is that once we got to like, I'm not gonna like show the actual moving of the discs, but the whole idea is that you could model this problem. Like you can move everything here. Now you end up with like a smaller tower here. Smaller tower, you just move this to here, right? You could model it using this recurrence relation. H of n is equal to 2 h of n minus 1 plus 1. Right. And the whole idea of recurrence relation is that you could use previous numbers to get a current value, but this doesn't really help us. Say I want a value for f of 100, right? I'm in a time crunch. I need f of 100 for some bizarre reason. Well, then using this formula, I can't get f of 100 until I know what f of 99 and 98 are. And I can't get f of 99 until I know what 98 and 97 are. And then, you see what I'm trying to say? Like, you can't obtain f of 100 until you go down the list. You obtain up until like f of 3, right? And you go reverse. Which is why, same thing here. We want to usually turn these formulas into something that's more closed. So for any n I choose, I just plug it in, and then I get a value. Right? Is everyone okay with that idea? The concept of... Anyone have any questions? I feel like I'm going too fast. Everyone good? Everyone's okay? Basically, the idea is we want to turn a recurrence relation, the formula, into a more formulaic formula, right? Where we just plug in n, any n, and then we just get a value. Okay. So there's one way of doing it, and they show it here, where it's kind of like you use a bit of logic and you try to like reverse engineer it. I'm gonna go over this. I'll go over this method real quick. Then we're gonna go over like those equations. I think like r times minus, like the C1, C2, those types of equations. So here we know that h of n is equal to 2 times h of n minus 1 plus 1. Well, h of n minus 1, we know that h of n minus 1 is equal to not 2, is equals to 2 times h of n minus 2 plus 1. So let's plug this in here. So we plug it in for h of this. We plug this in here, right here. And we get this. We get 2 squared times h of n minus 2 plus 2 plus 1. And you might be thinking, why can't we just write this as 4? We won't write it as 4 for now. Just to like see afterwards, we'll see a pattern. Right? So then what's h of n minus 2? H of n minus 2, that's equal to 2 times h of n minus 3 plus 1. Right? So we see here, we have h12, so that's important. h1 is 1. We see here 2 times this. We distribute, and we get 2 cubed times h of n minus 3 plus 2 squared plus 2 plus 1. And one thing I want you all to notice is that this 3 matches this 3. So right off the bat, you're starting to see some pattern. Right? And then we recursively do that. We keep going until we got h of n minus 3. Minus 3 is equal to 2 times h and minus 4 plus 1. And we keep going down the line up until we hit h1. Right? h1 then gives us this. And I want you to notice, see how like this, the exponent matches n minus what we're doing? So if we do, let's look at here, n minus n minus 1, this is, you distribute the minus sign, it's going to be minus n plus 1, and you get 1. So h of 1 is technically h of n minus n minus 1. Right? And that's why the exponent here is n minus 1. And we know h of 1 is just 1. This is just 1. Okay? So then we don't need to go any deeper. We get 2 to the n minus 1 plus 2 to the n minus 2 plus dot 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 plus 2 plus 1. This is just a, correct me if I'm wrong, is it geometric? Not geometric. It's one of the series you learn in calculus, and it's basically equal to this. 2 to the n. This is equal to this. Okay. And now we just turned this recurrence relation into a closed formula. So say I want h of 100, whereas before I needed to like plug in, get 99, 98, 97, etc. I just plug in 100 here, and I get a specific value. Is everyone okay with that? Does anyone have any questions about how this is done? This is how you get the formula. In order to like prove this is the formula, this is where you would use induction to then say, oh, whatever, for any n greater than or equal to k, it's true. Does anyone have any questions about this? Any questions at all? Okay, so that's one way of doing it. Yeah, right here. So I want 24. If I want to find out how much time it's going to tell me to do it, this is like a little myth with the monks and the gold discs. So 64 gold discs. It's going to take this long. This is a long time. That's why it's a myth. No one tries doing it. Okay. So these are just different applications of it. There's another one with the what it's called. Basically, when you try to find like with the roots and you have the different formulas, trying to find those. Does anyone know what sections there are? 8.1 to 8.3. Bingo. Linear homogeneous recurrence relations. Okay, does everyone see these, right? Everyone's seen these? She's went over linear homogeneous recurrence relations.
Yeah,
This is like another way. Sorry, what was that?
yeah, she did go for this.
Yep. So this is like another way of trying to find the explicit formula. Right? So the whole idea is that we have this recurrence relation. In this, I think most cases is gonna be the 2-degree. Like here they get like multiple degrees. So we have a recurrence relation. A of n is equal to C1 a n minus 1 plus n minus 2, yada yada yada. We're using these, focusing on the constants, C1, C2, up until CK. We could then create its characteristic equation. Once we create the characteristic equation, we solve for the roots. And using those roots, we could then create an explicit formula. So the case that you're most likely going to get is a two degree case, where it's only going to be like f of n plus f of n is equal to some constant 1 times f of present on the exam, nothing more than chapters 1, 3, and CLI 6, 8. I think so. Don't believe me. Let's take a look at our draw box together. Midterm. So you're gonna have truth tables, chapter 3, chapter 5, chapter 6, chapter 8. There you go. This is all that your exam gonna be. 1, 2, 3, 4, 5. Okay. If there's something else that you guys want to go over in the time we have left, I think we have 25 minutes left. After this, we could do that. Let's go over here. So we have f of n is equal to C1 times f of n minus 1 plus C2 times f of n minus 2. Oh, shoot. Before you guys leave, if you guys need to leave early, Lauren, could you post the feedback form?
Yeah, I'll post that right now. Yeah, if you guys can just fill out this form before you guys go. Let me just send that in the chat.
Yeah, please give the feedback. We need to know how we good.
Yeah.
Whoa.
Here,
It's
use this one. For some reason, it always has that weird URL defense thing.
Oopsie daisy. All right. Sure. If we have time after this, we could go over logical equivalences. So given this equation, C1 Fn minus 1, C2 Fn minus 2, we could then use the constants and get our characteristic equation. Right? And the whole idea is we then solve this characteristic equation for 0. And there's two cases. The first case is if we get two distinct roots. Right? So how do you solve for 1 is equal to 0? Easy. You either like factor it out or use the quadratic formula. Then you get R1, R2. If this is the case, then we could say that A of n, instead of using this recurrence relation, we could then use R1 and R2 and get an explicit formula for it, right? So A of n, instead of being equal to C1 A of n minus 1 plus C2 A of n minus 2, we get A of n is equal to alpha 1 times R1 to the n plus alpha 2 R2 to the n, right? Well, where alpha 1 and alpha 2 are constants. How do you get these constants? Well, we use the base cases. So we know that we're going to know that f of 0 is, say, some x, and f of 1 is, say, some y. We didn't use these values. We plugged them in here. We get a of, this is a, right? This is an a of 0 is going to be alpha 1 plus alpha 2 because R1, R2 to the 0 is just 1. So 0 is equal to alpha 1 plus alpha 2. And you get A1 is equal, oh, sorry, that's not 0, it's x. So x is equal to this, and we get y is equal to alpha 1, R1, alpha 2, R2. And now you just have a system of linear equations, which you could solve for alpha 1 and alpha 2. All right, let's see if there's an example here I could do real quick. Right here. Does anyone have any questions so far about this right here? This is the whole idea of, and remember, this is for if there's two distinct roots, which we'll show right here. Maybe an example will help. So the characteristic equation is going to be r squared minus constant 1, which is 1 r minus 2, right? And we have a0 is 2, a1 is 7. Okay, so let's do this as a simple algebra or pre-calc, whatever it is. You factor it, what two numbers multiply to minus 2 and add to minus 1? Well, that's just r minus 2 and r plus 1. Okay, because minus 2 times plus 1 is minus 2. Minus 2 plus 1 is minus 1. And what do we get? We get r can equal 2 and r can equal minus 1. Okay? So then our formula is going to be of the form a of n is equal to alpha 1 times r1 2 to the n plus r2, or this is alpha 2, times minus 1 to the n. Okay? And now we want to solve for alpha 1 and alpha 2. We use our cases. Alpha 0, a0. So a0 is 2. This is a0. 2 is going to equal alpha 1. 2 to the 0 is just 1. And minus 1 to the 0 is just 1. So alpha 1 plus alpha 2. And we get 7. This is alpha. This is a 1. 7 is equal to alpha 1 times 2 plus minus 1 to the n. Minus 1 to the 1 is just 1 minus 1. So instead of plus, let's do minus alpha 2. Okay, and now once again, it's just a system of linear equations. We can do, let's do the combination. It's going to be, we add both equations. We get alpha 2 plus alpha 2 is 0. That goes away. Alpha 1 plus 2 alpha 1 is just 3 alpha 1. 2 plus 7 is 9. Divide both sides by 3. Divide both sides by 3. We get alpha 1 is then 3. Okay. And once we know this, we could use the first equation. We get 2 is equal to alpha 1, which is 3, plus alpha 2. Subtract alpha 3 from both sides, we get alpha 2 is equal to minus 1. Make sure I'm correct. Yep. And then what do we, now we know what alpha 1 and alpha 2 is. Put them back into the formula. We get alpha, not alpha, a to the n is equal to alpha 1, which is 3, times 2 to the n. Alpha 2 is minus 1, so I'm just going to do minus 1 to the n. And like I said before, we have now turned this recurrence relation, where in order to get any value n, we need the last two, into a formula where any n, we just plug in n into the formula and we get a value. And there you go. Does anyone have any questions about this question? Any questions at all? Speak now or forever hold your silence. Is everyone okay with this idea of recurrence relations?
Okay, maybe for the last of the session, someone was asking for logical equivalencies in chapter 1.
Sounds good. Before we go there, I just want to like quickly bring up the other case right here. If there's one root, so it's like the equation R0, right? Then instead of using this formula, you use this formula, and the whole process is the same, right? So in this case, we have, I'm just gonna quickly go through it. 6 minus 9. We solved this is C1, this is C2. And we solve, we get the root is 3. And we get, this is going to be the recurrence relation, the formula. Using the base cases, we get this. Solving for alpha 1 and alpha 2, we get this. Right, so it's a similar process, but if there's only one root, so from our characteristic equation, which is this, we get one root. Instead of using the other formula we used before, we use this formula, alpha 1 times r to the n plus alpha 2 n times r to the n. Okay. Any questions about that? While I look for, where is it? Propositional logic 1.1, 1.3. Does anyone have any specific questions about propositional logic? Any truth tables? So you got like a couple that are like main ones. You got and, you got or, not, implies, and if and only if. Right? So think of this as like computer science. This is technically and is the same thing as and, or is the same thing as or. This is the same thing as not. Implication and if and only if are a bit different. You can't really program that, but this is basically saying given P is true, we want to show Q is true. Right? And this is this P and Q, P if and only if Q is the same thing, it's just different directions. So if P then Q, and if Q then P.
Do we have exclusive or no?
Do we have exclusive or? In truth tables, I don't think we do. Correct me if I'm wrong. Yeah, I think they're inclusive. You don't have exclusive or here. Exclusive or something else. Oh. Oh, here it is. This is exclusive or. Okay. Those are the main. There's also like some right here. This is the exclusive OR table, I think I'm mentioning. This is like I said, the conditional if P then Q. And I want to make a little bit of a important thing. If P is false, it's always true. Right? P implies Q is saying if P, then Q. If you get 100 on the final, I'll give you an A. If you never get the 100 on the final, all bets are off. I never lied. Right? If you got the 100 on the final and I didn't give you an A, then yes, come to my office hours and like scream at my head. I don't care. I'm wrong. But if you never got the 100, all bets are off. That's the whole idea here. I just want to like point that out. Right? That's why usually in implication, P implies Q, we usually assume P is true. Because P is false, the entire statement is true. And that really doesn't help us. Okay, and these are just like other ways you could see implication. So, yeah, they're here. If you get 100 on the final, you'll get an A. If you don't get an I, if you don't get the 100, you could get an A, but that doesn't mean I'll give you the A. If you don't get the 100, all bets are off. This statement doesn't apply anymore. If you get the 100, but I don't give you the A, then yeah, you'll feel cheated. Okay. So that's it. Then
Sorry, I was referring to the ones where you use the De Morgan's law and those ones to prove that both sides are equal. That one.
oh, here, right?
Yeah.
So if you want to, I want to just point this out. This is what I was trying to look for. Precedents. So different operators have different precedents. So like in a statement, you might see the case where you have like different logical operators, so like nots, the ors and ands and implications. There's a specific order you got to do it. It's kind of like a PEMDAS of logical operators. So not always goes first. And an or, whichever have the same precedence, but whichever one is seen first is kind of like multiplication and division. And then we have implication and implication in both directions, which once again, depending on which one happens first. So when it comes to proving logical operators, or like the equivalence of propositions, you could use truth tables. This is the most tedious and like maybe time-consuming version of doing it. Like this might be a little long, but it will, you could make mistakes, but the idea is if you end up with the same truth and false statements after each side, then both are equal. Right? So say I also want to prove De Morgan's law. So not P and Q is the same thing as not P or not Q. And then not P or Q, same thing as not P and not P, not Q. Okay. So this is De Morgan's law. Things Arish mentioned it. This is De Morgan's law. These two are De Morgan's law. De Morgan's law. Law. And if you want to prove it, you could write a truth table. I'm not gonna write the truth table. It's gonna take a bit of time to write it out and like show it, but just take these as fact, right? Basically, when you negate a statement, you flip the inner operation as well as negate each of the statements, right? So and becomes or becomes and you just not P and not Q. Okay. So anything else? Also, a bit of. I mean, you might see this, you might not. You could see something where it's like different things combined. So something like this. And she might ask you to like simplify it. So I have no idea. P or not P and Q and Z, right? You want to simplify this? Well, P or not P is always true. So 1 and this is always going to be true. True and Q and Z. This is true and this is always going to be whatever this is. This ends up being Q and Z. This is like a very simple example of it, but I just wanted to like show you an example of what she might ask. He'll be like, oh, given this might be an example of what something you might ask. Given a long like statement, right? Maybe I'll try and simplify it. And you might need to know important stuff like anything and not it is always false. Anything or not that thing is always true, right? Amongst other things. But I think that's it. Does anyone have any questions? Anything else they want to go over? Anyone have any questions about propositional statements? And once again, if you need to leave, please fill out the form. Thank you, Laura. Any questions? Anyone want to have any last topics they want to go over? We got 8 minutes to burn. Any questions? Counting bit strings. Is that in here? No.
Is that a
Is that-
topic on the exam?
I think that's chapter 6.
Chapter 6. Okay, I think bit strings and pigeonhole. Okay, let's do that then. Chapter 6. Counting, pigeonhole principle. Okay, so the whole idea of the pigeonhole principle is if I have k boxes, and I have k plus 1 objects to place in these boxes, then there's gonna be at least one box that has multiple pigeons or multiple objects. So if you have a little demonstration here, we have k boxes, we have k plus 1 pigeons. You see in every case, there's at least one box that has multiple pigeons in it. Okay. And it's useful because sometimes, this is a little corollary, 1 to 1. This is basically saying if you have a set with k plus 1 more elements, this set has k plus 1 elements, k plus 1 elements, and we're going to a set that has k elements. There's going to be 2 elements here that point to the same. It's the same idea with the pigeons. There's going to be 2 objects from this set that point to the same object here, and thus it's not 1 to 1. Right. And then you have other examples here, like if you have 367 people, because there's 366 possible birthdays, 2 people have to share 1 birthday. In 27 English words, there has to be 2 that begin with the same letter because there's only 26 letters in the alphabet. And she might ask, how many students? If the exam is graded from a scale from 0 to 100, yeah, there's 101 possible scores on the final. You need 102 students such that there's a possibility that at least 2 students will get the same score. Then comes the generalized pigeonhole principle, which is a bit more useful. If you have n objects placed in n boxes, then there's at least one box containing at least n over k objects. All right. So for this type of question, you might be asked like this. What is the minimum number of students required in discrete mathematics class to be sure at least 6 will receive the same grade if there are 5 possible grades, right? So at least 6 students receive the same grade means the smallest amount n over 5 can be is 6. So right here, if you have 26 students, then there's no other way. Like there's 5 boxes here. 1, 2, 3, 4, 5. Even if you have 25 students, right? There's a case that you could get 5 for each, right? You might be thinking, oh, well, then why not get 6? Then you could have 6 students, right? Then just all 6 students have the same grade. But we're always thinking the minimum number, right? This is like kind of like the worst case scenario. If 25 students are in the class and all 25 are split evenly, 5, 5, 5, 5, 5, then you just need one more student. Let's say this is right here, the student, to be in the class to ensure that there will always be at least one grade value, in this case it's C, barely passed, that has at least 6 students, at least 6 students. Yes, you could have 6 students in the class, all 6 get the same grade, and it's true. But we were trying to find the minimum number of students. We need at least 26 students for this. If you want to find that out math-wise, just do, oh, who's showing up 3 minutes before the thing ends? Anyways. And over 5, the roof must be equal to 6. Just drop it, and you drop the roof, and you subtract 6 minus 1, you get 5. Right, and then multiply both sides by 5, you get n is 25, and just bump it up by 1, so n is 26. Right. So let's give an example here. Say I have 10 classes. Are people joining for the 320 review session that's going to be happening later, or still for 220? Because if you're joining 2 minutes before the thing ends for 220,
Yeah, 320 session is not supposed to start till 1. So if you guys are in 320 and you're joining, we're just finishing up this session. If you guys are 220, don't worry, this is being recorded, so you'll be able to see the full thing.
and hopefully it should be out by Monday. We'll try and get it.
Yeah, I
Okay.
mean, it's being recorded now, so I'm just going to send that over and hopefully they'll post it as soon as possible.
Yep. So let's do a quick example. I have 10 containers, right? So 1 through 10. How many, let's say, gumballs? I like gumballs. How many gumballs do I need to ensure that that there is at least one container with 7 gumballs in it, right? So what does that mean? That means n over 10 has to equal 7. You drop the roof, you get n over 10 is equal to 6. Multiply both sides by 10, we get n is equal to 60. Bump it up by 1, 61. So if I have 61 gumballs, there has to be at least one container that has 7. Okay? And that's just the application of this. Right here. There you go. Any questions about the generalized pigeonhole principle? Before you guys leave, let me show you where the thing will be located. Hopefully it's going to be here. So you go to Learning Commons website, resources, CSCI resources. So if you click on 220, right here, Delaram. I think they're gonna add the row here because we only recently made the Delaram review session. So that Kathy will add it here.
Yeah, if you
That'll be
scroll
here.
up a little bit to the 212, you could see one that was posted from last week.
Yeah.
Yeah, so we just did that one last week, and you can just see like the YouTube link is right there. So all you gotta do is just click that, and this will be where you have that. So yeah, just go to the Learning Commons website and you'll be all set.
Mhm.
Yeah, so just please fill out the feedback form because we'd love to hear from you guys. If you have suggestions for future sessions or anything, because like we do this for you guys. We want you to do really well. So best of luck with your exam. And if you have any questions, feel free to book appointments with us at the Learning Commons. We have various tutors for CS220 as well as other sessions too. So if you have any questions in any CS or math subjects, feel free to take a look.
Thank you
Yeah.
so much.
Of course, have a good day.
You too,
Everyone, and good
thank
luck on
you.
your exam. For anyone here, well, I think everyone here for 220. So, is anyone here for 320? That'll be starting at 1. Hopefully not.
Yeah, we need a break. More like you, Suleiman.
Okay, so I'm gonna. Do you want to stop the recording?